Yes, madam.
Am I audible now? Our principal madam has joined, and one of our
Yes, madam.
dignitaries
We
has
can
also
hear you.
joined. Okay, Mr. Shankar Mukhopadhyay has also joined, one of our dignitaries. He is the speaker on 30th June. So let us wait for a register, madam. Welcome, Devanshu. শুনতে পাচ্ছ? Am I
হ্যাঁ
audible?
হ্যাঁ অডিবল আমারটা শোনা যাচ্ছে তো
হ্যাঁ হ্যাঁ একদম
ওকে ঠিক আছে
waiting for our principal madam. Principal madam has already joined. Okay, and our register madam. We'll
no
start the
problem. I'm just trying whether it is perfectly okay or not, and that's why I've just logged in 5 minutes earlier.
Definitely very good.
Hello, Navanita.
Madam. Hello. Yes, madam.
Hello.
হ্যাঁ
Sudhanshu. Hello.
Hello.
Can you hear me? Can you hear me?
Yes, madam, you are audible.
Actually,
আমরা
I
wait
joined earlier, but I want. Bolo.
waiting for Nidhi madam, and we'll start the session. Our speaker has also joined.
Okay. Today's speaker is.
Dr. Devanshu De.
Welcome, sir.
Welcome, madam. Welcome.
Welcome to the digital platform. So when the normality will come, then we obviously invite you to our institute.
Thank you.
Okay, sir.
নমস্কার, কোভিড-19 আন্তর্জাতিক প্রক্রিয়া এখন সারা বিশ্বে শুরু হয়ে গেছে। এই সময় নিজের বাড়ির বাইরে কখন বেরোবেন যখন খুব বেশি প্রয়োজন হবে, ফেস কভার বা মাস্ক পরা সহ ওরা ভিজে মুখ আর নাক যেন ভালোভাবে ঢাকা থাকে। সর্বোচ্চ জায়গায় কমপক্ষে 2 গজ আপনার শ্বাস-সম্পর্কিত চিন্তা পালন করুন। মনে রাখবেন সামান্য অসচেতনতা সমস্যা যেতে পারে। কাশি, জ্বর, নিঃশ্বাস নিতে অসুবিধা হলে রাজ্য হেল্পলাইন নম্বর তিনি এখন উত্তর দিতে পারছেন না। অনুগ্রহ করে পরে চেষ্টা করুন।
Okay, respected all here. Let me start the introduction as it is 2:40 sharp. Good afternoon to all the participants and the dignitaries. The participants are the respected faculty members and research scholars from different institutes of India. Am I audible once again? Good afternoon. Good afternoon, sir. Good afternoon, sir. Madam, Shivaji sir has also joined.
Good afternoon, Shivaji sir.
Good afternoon, sir.
Good afternoon, sir. You are,
Shivaji
sir,
sir,
you
good
are
afternoon.
muted. Sir, you are muted.
Oh, my mic is mute. Now I am out.
Yes, sir.
Good afternoon, sir. Good afternoon. And it is our privilege you are joining with us.
Yeah, it's our student who requested. That's why I joined.
Yes,
That
sir.
is
Thank you, sir.
Navamrita.
Thank you. Thank you
Thank
so
you,
much,
sir.
sir.
Thank you, sir. So our registrar madam has also joined. So good afternoon to all the dignitaries here and the participants who are the faculty members and research scholars from different institutes of India. I am Dr. Navamita Banerjee Roy, HOD of Electrical Engineering Department of Narola Institute of Technology. I welcome you all to the inaugural session and the first day of our 6-day faculty development program on research and technical challenges in energy and power system 2020. We know that the electrical power is the backbone of mankind, and one cyclone of the nature of Amphan made us realize how helpless we are without electricity, as the entire city of Kolkata and many parts of West Bengal went into darkness. That was the prime motivation of organizing this FDP. Our speaker today is Dr. Debangshu De, and I would take the privilege of reading out his brilliant career in brief. Dr. De, he received his graduation, post-graduation, and PhD degree in electrical engineering from Jadavpur University, and presently he is a faculty member of this department as well in Jadavpur University. He has published more than 50 research papers in international journals in the field of research, including 20 papers in IEEE transactions, and co-authored one book from Springer, London. He has 4 patents to his credit, one of which one is a US patent. He is the recipient of IA Young Engineer Award in 2014, TRE Research Excellence Fellowship from SERB Government of India in 2018, as well as Vishwesharma Young Faculty Research Fellowship in 2019, and 2 Best Paper Awards. His areas of interest are applications of signal and image conditioning and processing in electrical systems, condition monitoring of electrical equipment, non-invasive testing related to condition assessment. He is presently the Secretary of IEEE Kolkata Section January 2020 till date, and he is also chairing IEEE Signal Processing Society till date. He is also in charge of Measurements and Instrumentation Laboratory of Jadavpur University, and he is the joint coordinator of a research group under EP scheme of Jadavpur University. I would request now our Honorable Principal Madam to deliver the welcome address. Madam, please.
Thank you, Navanita. It is very privilege to be here. Our electrical engineering department has organized the faculty development program on a very emerging topic. As already HOD told that energy, without energy, nothing can be possible. So energy is very much essential. At the same time, electrical engineering is the core sector and it is very much fundamental things which is required. So looking at this, electrical engineering department has organized this FDP, and today's session, Professor Devanshu De is the speaker. However, Professor Shivaji Chakraborty is very renowned professor in the field of electrical engineering. So he has joined with us. It is our privilege. Our faculty members, staff members, students who are associated with this FDP, they will get information related to the field and they will be enriched. So I hope this workshop, this FDP will get grand success. In this platform, it is not fair to say something because more words, because Shivaji said senior professor, he is there. So I request Navanita Banerjee, please request her to say something. It will be better for all of us. Thank you,
Yes,
Navanita,
yes.
and thank you all the participants.
Sure, madam. I would request Shivaji sir to address the audience, sir, please.
Well, thanks, Navamita, and thank you, Principal Ma'am. Uh, yes, it's a very difficult time. All of us are passing through very difficult and 3.5 can't go anywhere. So we understand everybody that what sort of difficulties we are facing. And this type of programs nowadays we are organizing at various levels. And now probably this is going to stay. Earlier, people used to think that this type of programs may be a luxury, but now I am sure that in the years to come, these programs will be there. So it's a good positive step on behalf of your institute to organize this faculty development program, because as a faculty myself for now 35 years, I believe that faculty, if they don't develop on a regular basis, then it's a indirect death of a faculty. I still remember a little bit lighter tone when I was student, all the way back to 1980. So we were having a class, and I don't want to name, but one of our faculty, that time senior faculty, came and took out a, from the appearance of the note, we could see that that note could be of anything 10 years to 20 years age. And then started teaching us a topic which was recent developments in something. Now we made a of that, and even meet together, we sometimes tell that, see, this is how recent developments takes place. So I personally believe that a faculty, if they don't develop on a regular basis, then basically they don't deserve to be faculty, because we are not here to be a clerk of a bank or that whatever will come morning and then go back home in the evening and we are happy. If that is the case, then I think we should not have joined as a faculty. Faculties need to continuously upgrade themselves, and for that we need to have more and more updated information on what is going on in and around us, in our nation, in across the globe. So this type of program, because I am taking such programs at various levels, that people are readily agreeable to join. Because I remember that when I was in leading IEEE, when we had to have organize a program and get a speaker from a very far away place, they always are, I mean, very reluctant to come. Who will spend 3 days for one lecture? People do not have that much of time. But in this way, everybody is willing because they don't have to travel. So they can join from their office. Kamshu's dress very much in his home. And I think Navamita's, I can see also Navamita is probably in her home. But still, you see, we are all joining. This is the actually the new atmosphere we are getting. Try to, as much as possible, people from different walks of life, different industries. That is another important aspect, because industry people are very busy. They don't want to spend time for something which is not beneficial to them. Whereas if you call them and tell that just come for 1 hour and give us a talk on whatever you are doing, they will be pretty happy. So it's a very good initiative. I have seen the brochure as well as the schedule that you have sent me. What I suggest is that you may try something a little bit more on a broader size, because I saw the speakers, they were all from Kolkata. I consider myself also from Kolkata. Why not people from other states? Why not people from even abroad? I mean, since it is an online thing, what is stopping you? Only it is your effort. So maybe try it. You will get some very good speakers, and if you want help, that readily we can help. That means we can contact you, give contacts of people who will be readily agreeable. In fact, that way the faculties, because today in this inaugural program, I don't find many people. I find only 15 people joining. So when Devangshu will be giving outing that Devangshu plus 40, in that case, Devangshu will not be very happy to give all those talks. So try to get the people involved also. Because recently what happened, I gave a lecture in a college in Tamil Nadu. Just last week, I think Devangshu knows it. But there were very large participation, in fact. It was almost touching 100. I could see from the participant list. Another one I gave in Trivandrum, that was a huge one. So what I suggest is, we have to bring people into these programs. And for that, yes, the topic is important. At the same time, we need some of the faculties. So I wish all of you, including the college, very best, because we know that how difficult situation all our educational institutions are facing. It is indeed a Herculean job now to to manage the things. In fact, I just go tomorrow morning, there will be some problem which will be almost next to impossible to solve, something like that. So I know you are facing same problem, particularly principal ma'am, and a lot of decisions on a daily with the exams, what to do. I don't know, probably you don't have hostel, but I have a hostel where 6,000 students stay. It's an unbelievable job. I mean, how and what to do. So wish you again all the best, and Devangshu, all the best for your inaugural, or I would say the opening innings of this particular FDP.
Thank you.
So go ahead, but I may not be, because I have another coming.
Sir.
So I may not, yes, I may not be able to
Sir,
stay.
thank you, sir. Sir, one thing I need to say, sir, we are 15 only here in the Google Meet. It's
Okay.
been broadcast in the YouTube, and there are more than 100 participants watching this live session.
Okay, so that information I was not having. So it was through
Yes,
through YouTube broadcasting. Okay.
yes,
All
sir.
right. Then that means that it will be already recorded, and it
Yes,
will
sir.
be.
It
So
will
we
be
should not,
available, sir.
that I can understand, because it is in YouTube. Then definitely it will be available. So all the best, and have a nice FDP. And I will join on Thursday, right?
Yes,
Yeah.
sir. On 2nd July, you said.
So Devangshu, all the best. Carry on.
Thank you, sir.
Thank you, sir.
Thank you, Shivaji sir. Thank you. Thank you very
Okay.
much, sir.
Namaskar.
Devangshu, before we proceed further, I would request our register madam is also there.
Okay.
Nidhi madam, can you say a few words, madam, before we start the session?
Thank you so much, ma'am. So a very good afternoon to one and all present here. This 1 week FDP on research and technical challenges in energy and power system with a galaxy of academicians and industrialists is definitely going to give a high quality learning to all the participants. I humbly convey my congratulations to the Department of Electrical Engineering for organizing such a wonderful program on the emergent topic, as well as this is the first time when YouTube streaming is going on. So thank you so much, ma'am, for organizing this so wonderfully. Thank you, ma'am.
Thank you, madam. So I would now request the speaker to start the session.
Thank you, Navamidadi. Thank you, Principal Madam. Thank you, Register Madam, and all the audience. And thank you very much from the bottom of my heart for inviting me for this particular FDP. And I'm really very happy to be here and speaking something on my research topic and sharing my experience with all of you. Am I?
Devanshu sir, myself
Please.
principal, with your permission, may I leave? Actually, I'm not in this field. I have some official job.
Oh, no, sure,
I
no
am in
problem.
the office.
Okay.
So with
Okay,
your
sure,
permission,
sure.
I am leaving, sir. Okay.
Sure, thank you.
Thank you very much, sir. Thank you very much, sir.
Okay, thank you. So I'll just proceed, just beginning my talk. So I am sharing the screen and sharing the presentation now. So probably, is this visible?
Yes, it's visible.
Okay. So the topic for this particular FDP I have chosen, that is the recent trends in condition monitoring of electrical systems. I have seen I have seen the different speakers in this particular program, and I have seen myself, Professor Shivaji Chakraborty, and also my senior, one of my senior colleagues, or we can say my senior researcher in our lab, that is Professor Prithviraj Purkait. And so most of the cases we may be discussing on the same topic related to this electrical systems, but I have chosen this condition monitoring of electrical systems, giving emphasis particularly on the condition monitoring of power transformers. There are so many electrical systems out there that can be just taken care of by the condition monitoring. But here we are going to concentrate on power transformers only, to just concentrate on a particular topic and have a focused discussion. Here in this slide, you can see condition monitoring that can be classified into two mode of operations, or two, we can say, functional parts. One is the data acquisition. That means if you are trying to have the idea of the condition of some electrical equipment, you have to have some data. On the basis of the data, you can decide upon the condition of the particular system. So data acquisition is one important part. And the second part is analysis and decision support. That means what to do with that data, or how to process, or how to get the final result or final condition of the particular system. So analysis and decision support is another functional part of the condition monitoring. As far as my discussion or this particular lecture is concerned, I will be just giving emphasis more on the analysis and decision support. Data acquisition is important, but for the power transformers, that condition monitoring, those parts, I think that will be covered in detail in the lecture of Professor Chakraborty. Myself. So whatever I am just going to present here, many of these particular of these works is done actually under his guidance. Some part some part of these works that I'll be just showing you, they were done during my PhD work, and some later on. So I'll be having emphasis on the analysis and decision support for the condition monitoring. And again, I'm just telling you that we are just giving emphasis on the condition monitoring of power transformers mainly. So this is one typical curve that is important related to transformer condition monitoring, that is transformer failure pattern. And this is called the famous bathtub curve. and you can see that initial failures are somewhat are there. The failure rate is in the y-axis and the time is in the x-axis. This curve, this particular curve, that is wear out failure, that increases over time. That means longer the transformer is in the service, more probable it is to be for the failures. And the early or infant mortality failure, that reduces with time. That means during the manufacturing process or something like that, there are some problems inherent to the transformers, and with time that infant mortality failure, that reduces. And the combined curve of all those, that means if you have so many large number of transformers, then if you just plot the overall failure rate, the combination of these two curves gives you these bathtub curves. Now we can see over the middle region, the failure rate is less, but over time the failure rate increases. Now, as far as our power infrastructure is concerned, most of our infrastructure or transformers that has been installed there, they're almost at the edge of their designed life. So now they have reached this third portion where the failure rate increases. So that is why initially people tried for the time-based maintenance. We call it TBM, time-based maintenance. And now we have just shifted that towards the condition-based maintenance. That means we have to analyze the condition of the particular system or the transformer over time, and then you can have the condition, and depending upon the condition you can fix what is to be done with that particular transformer, how vulnerable is it. So that is why condition monitoring or condition based maintenance is nowadays very important, I can say. Here the transformer condition monitoring, as I told you that I'll be giving emphasis on the analysis part of the data. So therefore, this is one of these structural block diagram that will give us the idea of the flow of the particular condition monitoring job. That means the raw data from sensors, we have to get some data. Then we have to have some statistical analysis and model estimation, then diagnosis algorithms for recommended actions, and then maintenance information. These are some of the procedures, and they can be included or programmed in an expert system. And the monitoring part is this part, that is raw data from the sensors and qualifier assignment, and then we can have the trend and the alarm and diagnostic part, that is there, that is expert system based, rule based, and computational intelligence processing and computers maintenance and management system, etc. They belong to the diagnostic part. So first of all, as even though it is not the main focus of my talk, but we must have the idea of data acquisition, because what are the things we are going to use in the case of analysis, we must know what are the basis of that. That means what is the philosophy of choosing certain tool or certain algorithm for the analysis. If we do not know the data acquisition, what are the limitations, what can be the things that we should be taken care of, then we cannot design the proper signal analysis thing. So that is why, even though it is not the main focus of the talk, I'll be discussing say a little bit about the data acquisition for this type of thing. Say for example, say if we are trying to say have the transformer condition in terms of say and the impulse response. It is a typical test for the transformer. It is not the routine test, the type test. So whenever the manufacturer say demands that the transformer should have the enough capability or insulation to withstand the impulse waveform, so then we have to perform this type of waveform. The simple thing to say is that we have to apply some impulse voltage across the transformer winding, and we have to check what is the response current, and from that current we have to understand whether there exists certain flaw or certain problem in that particular transformer winding or not. This is one typical transformer impulse data acquisition setup network. This is the impulse from the search generator, we can say, that can be given to the transformer, actual transformer. In our lab, the data I'll be showing that is on the real life model of the transformer. That is why it is written as transformer model. In real case, that model will be replaced with real life transformer. So the surge or impulse that will be applied across the transformer winding and the voltage waveform, that we have to see whether that particular waveform is as per standard or not. Then we can have that voltage using the potential divider, that because that impulse voltage will be of very high magnitude, directly you cannot record that using a CRO. So that is why you have to use some potential divider, as well as we can use some current shunt or current acquiring device, so that we can record the winding current. So this voltage and current, we can analyze them, and then we can have some processing in PC with some communication, data communication channel. We can transfer the data to PC, then we can process that data in the PC, and we can have the result. So usually we use in our lab capacity potential dividers. These are some capacity potential dividers ratings on figures to have a look and feel the idea of this. And some practical examples that we are going to cover in this particular topic is that data acquisition technique for condition monitoring of transformer mainly, that I have already mentioned. And also we will be discussing some partial discharge signal analysis, and also the sensing data from leakage currents of high voltage insulators, that we will be going to talk about. So first of all, as the topic is the recent trend, so the recent one of this particular recent trend that I must mention is this one, that is called the polarization and depolarization current measurement. Again, I am saying that I am just mentioning this. Detailed may be covered by Professor Shivaji Chakraborty, as I have seen the topic of his talk. So I am just mentioning as I am discussing about the recent trends. So this is one of the very much recent trends or topics on this domain of research. So that is why I am just discussing this. So it is called the polarization depolarization currents, called PDC. And PDC measurement is that is usually offline, and we can have the overall insulation condition for a particular transformer using this method. Say, we can have two types of information or condition assessment. For example, if we are discussing or if we are interested in, say, some point or some condition of insulation at some particular point, that is one way of finding out the condition of an insulation. And another way of not the information of a particular point of the insulation, but the overall estimate. So this PDC or polarization depolarization current gives us the overall measurement of the or overall condition of the transformer winding. So how it can be done, we can see. Say this is one transformer, and there are three figures. We can see A, B, and C, all giving the schematic of transformers with different types of windings. Usually I have covered most of the all of the types of windings that we can encounter in real cases. So here you can see this, in this case, the low voltage winding and high voltage winding, they are basically shorted, and they are forming two electrodes. Similarly, here also low voltage and high voltage winding, they are just shorted and they are providing two electrodes. So from circuit point of view, what we are getting here, if we give some voltage here across electrode 1 and electrode 2, is that it is basically a capacitor charging sort of phenomenon that will happen. Why? Because you can see conductors, this low voltage winding, that is basically conductors, again the high voltage winding, that is the copper conductors, and in between them there exists certain insulation. That means this insulation, we are trying to find out the condition of this insulation. That means if we are trying to find out the condition of the transformer, we are mainly interested in the condition of the insulation of the windings. So therefore, This electrode 1 and electrode 2, if we take these two electrodes as the two plates of the capacitor, and then the insulation will be in between these two electrodes. So if we give supply some voltage across this, there will be some charging. And again, if we short circuit them, what will happen? That particular insulation which is being charged, that will discharge. That means there will be some capacitive discharging. So that is why the term is called as capacitor, that is called polarization and depolarization current. Polarization means charging current and depolarization means discharging current. And from that current, we can have one of this type of model. For example, this is, we can say, the model that can be discussed. That is not important for my particular topic. But the thing is, what we are trying to find out, that we are trying to model that insulation. That means it is basically RC charging and discharging. So there will be several RC branches, and condition monitoring of transformer insulation means we have to find out different values for our RC, etc. And from those values, we can predict what is the condition of the insulation. That means more say clearly we can say this is the winding. As we have taken electrode 1 and electrode 2, across electrode 1 we have given that DC supply and high voltage, and then say of the order of say few kilovolts, then we can record the current, and that current will be something like this. Whenever the voltage is say high, that means this voltage sort of a step voltage of the order of say few kilovolts, then the current will be something like this. This is IP, this current. This current is something like the charging current. And when the voltage is shorted, basically that capacitor means the capacitor formed by the insulation system of the transformer, that will discharge. From that charging and discharging current, we can have the model. That means this model will give you the response similar to this, and from that particular model, this model, we can have the idea of the condition of the insulation by knowing the values for these parameters. For example, C0, R0, R1, C1, R2, C2. That can be different way we can model them. Okay. So the problem is we can have the very low level data acquisition. That means low level means if we are trying to record the current, this microampere, or we can have the current of the order of say nanoampere if your insulation is very good. So this current will be very low. So one problem is that we should have some denoising mechanism. Otherwise, you cannot have properly denoised data, because as your current is very low, so of the order of say microampere or nanoampere, they are more susceptible to the noise contamination. So therefore, one important aspect of doing this data acquisition is that we have to denoise that. So we have developed in our lab during our old days this setup. This is the voltage supply, and this is one contactor that will switch on the voltage supply and switch off, and that means the switch on means charging, switch off means discharging. In terms of PDC, switch on means charging, means polarization current, and switch off, discharging, means depolarization current. And we have say just in our laboratory purpose, we have just made one test cell that is there. In practical purpose, that test cell will be replaced by real life transformer as in this figure. This you can see, this is a suitcase, pretty VIP suitcase commonly used for local traveling. And that suitcase, there is one typical prototype that we have developed, and that we have recorded the data in on real life transformers. And it is customary, and we have just developed that in our Jadavpur University. It is during my PhD work, and it was done under the guidance of Professor Shivaji Chakraborty. So this particular thing, it is customary to blow our own trumpet if you are given one chance to deliver a talk. So it is very common to just blow your own trumpet. So I am doing the same thing. So we have granted one patent for that, and the patent is for this prototype that I have shown you. And these are certain real life data, and you can see for different colors mean different condition of the insulations, and different condition how to analyze them at different temperatures. The waveforms, those current waveforms, they vary at different conditions. You can see this picosiemens per meter there. The conductivity indicates the condition of the insulation. So these are the waveforms, and data acquisition has a role to play for giving us proper data to get proper information. So why I am showing this is that usually the basic while doing research work, the basic focus of any researcher is towards the analysis part. But what I am trying to give emphasis is that it is not the analysis part. It is basically the most important part. It is the data acquisition part. There is nothing more important than a good data. So that is why whenever we are trying to give emphasis on a very sophisticated analysis tool, we must know the background of the data. That means how it is being collected, what are the say important aspects, what are the important things we must remember while we are just recording the data. So that is why unless we do not know data acquisition part, we cannot choose the proper analysis tool. To emphasize that, I have just shown this one because it is not actually the main focus of my talk. But unless we are having, because nowadays I can see many of our researchers, many of our students, they are very much fascinated about the soft computing tools and the analysis softwares on that. The hard work, that is the data acquisition part, they always think that okay, data somehow that will come, and on the data it is the duty of the sophisticated tool, how sophisticated tool I can use, then that the performance depends upon that tool. But I can assure you that it is not the case. Whenever we are trying to solve a problem of this type of condition monitoring, the first and foremost thing is the data. As your data, if your data is very good, then you can have proper information, then you can analyze properly. Then tool sophistication of tool is somewhat okay. For some cases that is good, that will be helpful, but not always. Not even this kind of cases where your current signal or the response signal that is of very low magnitude. So that is why once we have decided to go for an analysis of the data, we must know the background of the data. That is the main thing that I am trying to give emphasis. The second thing, the data acquisition for part for my discussion, that will be another thing is the partial discharge. We know that partial discharge means if there exists some void in the insulation of some say transformer. I'm just discussing about transformers, so that's why I'm giving example of transformers. So if there exists some void within the insulation, then what will happen? There will be some discharge, local discharge, and that discharge that will hamper the insulation condition. You can see in this figure A, there are some black spots. They are just burned out the insulation. There will be not total failure between the electrodes. The insulation may not fail completely, so it is not a dead short circuit. It is a partial short circuit, we can say, but it is called a partial discharge because it is a local discharge in that insulation. And as and if and you can understand easily that if it going on happening say 24 hours inside the insulation, what will happen? It will damage the insulation. So that the effect of PD or partial discharge on insulation is it will degrade the paper, and there can be formation of this sort of tree, and those tree will gradually make the complete breakdown. So condition monitoring for a particular electrical equipment, say transformer, this kind of partial discharge signals are also very important. If you find some partial discharge signal, you can you should be very careful about that, and you have to try to mitigate that. So this is one type of say data acquisition setup. where we can get the data. Again, this is the, say, it is not impulse wave, it is a power frequency. And if we have some void, we can just showing our data action setup for our laboratory. That's why it is sample. In case of practical use, that will be a real life thing, a real life equipment. So within the sample there exists some void, and due to the void there will be some discharge, and that discharge will create some electromagnetic pulsation, and that electromagnetic signal that will be captured by this network, and that will be recorded. And what sort of signal we can get, I can show you in this diagram. If partial discharge occurs, you can see it is almost buried in noise, but there are certain high peaks, high rises there and there, that will give you some idea that there may occur some partial discharges. But if you look at in the say real life sinus over the sinusoidal waveform, then it is very difficult to identify in which case it is a partial discharge and which case it is really the noise. I have magnified it, so that's why it is seen it seemed to be a band of noise there. So just try to understand the challenge. Challenge here is the partial discharge signals, they can well be buried in noise, they can well be contaminated in noise, and you have to remove the noise. So what sort of thing we can apply? Again, another blowing of trumpet, that is we have just designed this particular setup, this the right side, and we have just got one patent on that partial discharge. And the third one of my topic, initially I am just discussing about the data acquisition part, then we'll just discuss about the philosophy of why you have chosen this type of analysis softwares or analysis tools. That is why I am just spending time on giving you the idea how the data has been acquired. Otherwise, why I am using those sort of tools there, that won't be very much understandable. So the third topic is, say, the condition monitoring of remote high voltage insulators. You know that there are so many insulators. There may be a lots of insulators in that say our transmission or distribution network. There are so many overhead insulators, and it is very difficult for manual checking of each and every insulator. So that is why what is done or we have planned to do is that we can have a remote monitoring system, so that we do not have to check the insulators manually. We can check them over the mobile network or cellular network. How we can do that? This is one of that particular model of that. See, this is one, say, electrical network, and we are having so many insulators like this. This is the high voltage line, you can see this is the earth line, and in between that there exists an insulator. If the insulator over time becomes aged, and it there becomes a complete failure between high voltage line and earth, then the complete line to ground failure will occur. So that is why if we can have the condition of the insulator, that means before total breakdown, we can identify what is the condition of the insulator, then we can we can replace that faulty or aged insulator in time, so that we can prevent the failure of the network. So the idea is there will be some modules we can install there in the insulators, and from that module we can transfer the data to the using the cellular network to the control or administrative or the analysis building. So we have just made one prototype for that. This is one insulator, and that insulator, the lower one is the earth link or the earth line. So in the earth line we have just set this particular module, and that module is acquiring the leakage current. Leakage current means the current that will flow through the surface of the insulator to the ground, and as this insulator having that resistance very high, so the surface leakage current will be very less, of the order of say milliampere or microampere order. So therefore, whenever you are recording that current that will give you the condition of the insulator. How? Like this. Oh, this is our developed module that this mobile phone is being used for to receive the data, and this is one type of data that we have collected. And how we can have this? You can see the left one, the leftmost one, this waveform that is for early aging. That means it is not very aged. So the leakage current through this leakage current here we can have like this. I am saying that it is leakage current, but here amplitude voltage is written. That is little bit confusing maybe. I am explaining that because I've shown you that in this module there exists some shunt. So basically we are not directly measuring the current or directly recording the current. The voltage drop across the shunt, that as it is a resistive shunt, so therefore we can have a voltage waveform similar to what voltage drop across the shunt, that will give us the waveform of the current, so or nature of the current. So this is the nature of the current, and whenever we transfer it over the cellular network, what we are going to get is the left one. And you can see it is quite distorted because the cellular network has its own modulation and modulation methodology, and others, say others amplifiers, etc. It has their own characteristics, own frequency spectra. So therefore this particular waveform that will be modified like the bottom one. So the top one, this one is our recorded on site. That means the data that will record here in this module, that is the top one. But the bottom one is the data we are going to get. So here the background is that the top waveform, the top one, had it been this, if we are able to get this data, this one, the early aging, then moderate aging, then late aging, they are quite distinctive. So therefore we can distinct or we can separate them easily. But whenever we are trying to use the cellular network, what happens is that their distinctive features, they are somewhat lost, and it will be very difficult for us to analyze the condition getting this data or the bottom data or the data we are receiving over the cellular network. And we just found just one US patent for that, for this analysis part. So now I have just told you the background of three, or I just shown you three examples or three cases where we can get different types of condition monitoring data. Now we have got the data, so what to do? Now I'll just show you how to approach the, or what was our basic motivation for choosing certain tools, or how to analyze that. That is the basic thing I'm trying to just highlight here. So condition monitoring problem, I told you here, the first part, that was the data acquisition part. The next part, that is the data analysis part. And analysis part, we can again divide into two types of functionality. One, we can have some features. Some feature we have to extract from the data. We call the step as feature extraction, and from the features we have to classify the condition, and I'm saying that as the classification stage. So condition monitoring problem can be divided into two parts. One will be your data acquisition, second part, that will be your analysis. And again, analysis can be divided into two parts. One will be your feature extraction from the data that you have got. Then you have to extract some features, and then you have you can classify those features and you can get the condition, provided the data is noise free or properly denoised. That is, I have told you earlier also, that was the problem, because many cases the data was of very low magnitude. For example, I gave example of that PDC curve, that is also of very low magnitude. And again, the data for the leakage current, that is also of very low magnitude. The partial discharge data, that is in terms of say discharge pulse. So in the that pulses are also very very low magnitude, even though that charge that will be we are going to measure, so that can be measured in picocoulomb, or but whenever we are just recorded that in terms of voltage, so that voltage will also be very less. So what is the solution? So solution, we can just how to attack the problem of designing a say analysis software. So how to tackle the or attack the problem? So we must have two stages. One we call that is the rule generation phase. Rule generation phase means there may be several sensors. Several sensors, maybe one sensor, two sensor, or maybe several sensors. That is a general form. That is why I have just shown say sensor A to sensor N. Then the data should be pre-processed. Why pre-processed? I told you, because of the noise, etc., those problems. There can be scaling problem. So therefore pre-processing will be there. Then we have to have some feature extraction. Then we have to have some rule generation phase. We have to generate rule, and using the data we can have some training data and testing data. So by using training data you can generate the rule. By using the testing data we can validate the rule, whether the rules are validated or not. I have not shown the feedback loop. That means if your rule is not performing well, or the performance of the your analysis tool is not very good, then you have to repeat the steps. So after completion of the or after validation and having successful or acceptable performance, we can have the decision rule base. Now in the operating phase, what will happen? Then we can readily use the decision rule base, the pre-processed data. From that data we can have the feature extraction, then the feature vector will be fed to the rule base, and then we can assess the condition. We have said that impact assessment, that is the term used usually in case of sensor fusion, and that impact assessment can be done, and we can consider this impact assessment as our condition assessment of the insulation. So the first example I'm just showing, I have shown you three examples. One for the impulse waveform analysis of transformer, then that partial discharge, and then the that online, cellular network based remote monitoring. So here the same diagram, the data was actually recorded as per IEC. This is the IEC number. In this particular IEC, the testing procedure is described. According to that standard, we have to apply some voltage, and we have to record some data, and we have to know what is the condition of that. See, I have just taken two examples. One is the real life analog model, and other is the digital, or EMTP is a software for transient analysis. Probably all of you know. So using that model we have recorded. And this is the one particular model of the transformer in our lab. And this is the oscilloscope and the surge generator. We have given some impulse voltage waveform and recorded the data. And as it is a model, we can create the fault at different places. That means in real life transformer, what is the problem? In real life transformer, manufacturer will not disclose the design specifications and other details of the transformer. So that is why when you are going to design a system that will predict the condition of the insulation, we have to test the system on some transformer model. And this one is the transformer model, where we can create deliberate faults in certain windings. Deliberate fault means we can short circuit two windings. If insulation failure occurs, what will happen? If insulation failure occurs, then a coil, the different winding, different turns of the coil, they will be short circuited. So therefore, the condition assessment means we are trying to find out, is there any fault in the winding? Are there different turns of the windings in the transformer are there present there, so that there occurs certain insulation failure, or they are short circuited? How? By looking into the current waveform. Just look there. Say this is the winding, and the winding will have some say turn to turn capacitance and say some capacitance between the winding as well as the ground. So this CS means the turn to turn capacitance and CG. Now if the fault occurs, what will happen? That capacitor will be short circuited, so there will be no such CS, only CGs will be there, so there will be some change in the circuit. So if there occurs some fault, there will be some change in the circuit, so there will be some change in the response. That fault can be of two types, either series or shunt. Shunt means that CG will not be present, and series means that CS will not be present, because turn to turn shorting of the winding will occur, and for shunt the winding to ground there will be some shorting. So therefore these are the two typical types of faults that usually occurs in the transformer winding, and the response curves look like this. You can see A and B just shows the series fault at different disks, different locations. And you can see the two waveforms are very similar to each other. Their nature are very similar. They are different. We can distinguish them by naked eye, but it is very difficult to set one rule base for them. So that is why usually what we give emphasis on that. First of all, the waveforms can be denoised. But most importantly, we should go for some handcrafted features, usually, most of the cases, where we know what are the basic features of the system, what are the things we are trying to look into. So features can be of two types. One, that can be learned by a system, and you do not know what are the features your system has learned. And the second type, you know what are the features you are trying to learn. That means they are basically predetermined features, and we call them handcrafted features sometimes. Nowadays, probably you have heard of, and the researchers are very fascinated using different types of soft computing tools. For example, artificial neural networks, say nowadays convolutional or deep learning networks are very popular, deep learning networks. So whenever you give this type of waveforms input to that type of system, say an ANN or say a deep network, what happens? They learn their own features and you have no control over it. Your network will perform very good. That means it can say what is the type of fault after training. But what is the problem? Problem is that as a user, you do not know what are the features it has chosen. So that is the main problem of using, say, such networks. So while we are designing one analysis software, our first approach should be using some handcrafted features, or at least know what are the features the network is learning. Otherwise, it is sort of a black box. That means your system, you are giving some input to the system and your system is giving some output which is good, but you are not sure why or how it is performing well. Now, one question is usually asked nowadays to make you understand the situation. For example, say there is one, say, robotic operation in a hospital. Consider there exists one robotic operation facility. The robotic operation, the machine operates, and say an appendix that will be operated by a robot. Okay, appendix is a very easy operation. For example, open heart surgery. Open heart surgery that can be done by a robotic operating machine, and it has the success rate of 90%, say. And there will be some the manual or surgeons, human surgeons, expert doctors are also available. So doctor can also do the surgery, but as human surgeons, the accuracy level is, say, it is given slightly less than that, say 80%. So you have to choose between these two. That means one will be the machine with higher percentage of accuracy, but you do not know how and why the machine performs well, and you know an expert doctor, but for the manual operation, the rate of success is 80%. Which one should we choose? So that is the basic dilemma, or that is the challenging thing nowadays in this type of analysis or say machine learning problems. That means usually we are happy with this. Say most of the cases students or researchers are very happy getting data, so they are trying to use some software tools to analyze the thing. But the problem is this one. That means we have to decide upon, that means how to use the tool or which tool we should use. That means one tool like a black box giving you very high accuracy, but you do not know what is happening inside, what are the features it is learning. And again, to understand the thing better, should we go for known features? And we should say yes to that. That means we should learn what is the system is learning. So that is why sometime if you know what is the system learning, that means on the basis of that it is deciding, then you can design your own features. You can improve the performance. That is why handcrafted features are very important. Here it is another waveform for the shunt. Again, you can see the two waveforms are different, but not as much as different between them exists, so that you can readily say this waveform for the shunt fault at this number 50, this one for this number 80 or so. So again, it will be fault identification, that is feature extraction and classification. And for feature extraction, I am just giving you one example. We can choose cross wavelet transform. And again, the question comes, why? I told you that the system, the data should be properly denoised. Now in cross wavelet transform, if your data is random, if your noise is random, then cross wavelet, cross correlation sort of thing will happen. And you know that the noise, if they are uncorrelated, so therefore what will happen, whenever you perform the cross wavelet transform, the effect of noise will be eliminated. So that is why I told you that which tool you should use. To know that, to understand that, we must know the background. It is not that data acquisition, whatever may be the data, I can try different methods, I can try different tools so that we can have different results. It is not the proper way to learn. But we should know what is the background, what is the data, how data has been collected, what are the limitations, what tool we should choose. That is why the cross wavelet transform can have the facility of eliminating random noise. Okay, these are the equations. Equations are not very important. What important is that is the physical meaning of this. Physical meaning of this is that if we perform cross wavelet transform between two signals, for example, this is S1 and this is S2. If we perform cross wavelet transform between these two signals, say S1 and S2, what will happen? We can get this type of a graph, this type of a diagram or image. So what is the meaning of the image? Meaning of the image is that it is sort of wavelet transform. Wavelet transform gives us we can say the representation of a wave of a signal in time and frequency domain. That means at which time which frequency exists, that it can tell you. Now cross wavelet transform tells you that S1 and S2 in which time frequency zone they are having in common. That means in which time, in which frequency both of the signals are having in common. That means I have told you, that means it gives us the cross wavelet spectrum shows the regions in time frequency space where two waveforms having high common power. So having high common frequency content, it gives red. For example, higher value means red. So in different regions, red and yellow regions, that indicates in those regions two signals are similar. And blue regions means in those regions, in those time frequency regions, these two signals are different. So you can have a closer look of this waveform. And the arrows are, you can understand, if we perform Fourier transform, the Fourier coefficients are complex. So therefore they are having some magnitude as well as angles. So the same thing happens for this wavelet transform also. The wavelet coefficients can be complex, and if it is complex, then it has some magnitude as well as some angle. Angles are shown by the arrows that you can see in this diagram. So the red and yellow regions means higher common power between two signals, and the blue regions means low common. That means their common that particular time and frequency, they are not matching for those signals. So therefore, using this diagram, we can compare the condition. For example, we have this S1, this diagram. For example, this S1 is a faulty waveform, and this S2 is a pre-recorded waveform that is showing you, say, some fault at position, say, A. So if these two waveforms having, say, some common power higher than some threshold value, we can say this signal can be representing a fault similar to S2. In this way, we can analyze them. So that is why from this is the cross wavelet spectrum, and from this spectrum we can extract certain features. You can see F1, F2 to F12, some mathematical equations are written. Equations are not important to understand this, but you can have some, if you look into these equations, you can find they are sort of, say, one-dimensional moments, etc. For example, centroid, for example, say, first order moment, second order moment, like that. We can say these are some statistical features of this. That means we have two signals, we performed cross wavelet transform, and after cross wavelet transform we got this, and if we are getting this, then from this signal, from this picture, we can extract certain features. That means we can have this kind of a feature. Otherwise, the entire of this matrix or entire of this image we have to put into. The outcome of cross wavelet transform is a two-dimensional matrix. Two-dimensional matrix means row may indicate the, say, frequency, and columns may indicate time, and for a particular entry that gives that particular coefficient value. That means, say, row 1 column 1 gives, say, for a particular time, for a particular frequency, what is the coefficient value. Coefficient value means what is the common power. If the coefficient is high, we can say S1 and S2 is having common power very high in that time and frequency. Just like that. So there will be a very large size of the data if we perform the cross wavelet transform. So if we are trying to give this particular entire waveform to the system will be very computation intensive. So that will be heavy. It will be, you require much more resource to process the data. If you are doing this in your computer may get hang, because it may go out of memory, because a huge amount of data you have to load. So that is why, to reduce the data, we just extract certain features. And this type of features we called handcrafted, because we know what are the things we are trying to find out. Had it been in this way, that means if we give this entire waveform input to a network, what is done, usually done in case of deep networks. Deep networks uses very high memory requirement. They use very high memory or very high performance computers. So if you give input this particular wave, this entire image to that, it will process, but you never know what are the features it is learning. So handcrafted features indicates you are more confident on the system or inherent features or inherent nature of the system. Nowadays, people are also trying to decode the black box also. That means if a particular ANN or a CNN or say a deep network is giving you some performance, people are also trying to decode that. That means why the system is giving good performance. Why? What are the things it is trying to learn? Just like that. So we have got the features. Then we have to use some classifier. For example, in our case, we have used rough set theory. Again, the same question comes, why rough set theory? Again, that will give you the basic philosophy of choosing a particular tool. For example, say I have just shown you this figure, these features. That means I told you that these 12 features performed very well in my problem. My problem means that is the identification of fault in case of impulse. Now, say your problem is somewhat different. For example, you are trying to identify, say, some power quality event. So, in case of power quality event, are these features helpful? You do not know. For example, you have seen this kind of handcrafted features performed well in some problem, but you do not know whether they will perform well in your problem or not. So that the same thing happens here also, because before doing the thing, we have idea that all of those features, they will give us a very good result, or all those features, they are equally good. Maybe F1 is very good feature I have chosen. Maybe F11 is not that good. How to understand that? So that is why rough set theory, you have chosen this type of tool that can give us the basic idea of importance of each feature. That means whether all of the features are good or not, this kind of information we can get from this rough set theory. So for rough set theory, we do not require any a priori knowledge. That means for your problem, if you are trying to use my features, then there is no hindrance using rough set theory as a classifier. Why? Because rough set theory doesn't require any a priori knowledge that which feature we should feed into. But for handcrafted features, it is better if we have some prior idea that these kind of features can be better. How to know that? Usually that is why we study different research papers. That means for similar problem, what are the features other researchers have used? But again, there is no guarantee that the features used for problem A can also be used for problem B. That means your problem. So rough set theory is good in that aspect, that you can give so many features. Some features may be good, some features may be bad, and rough set theory can discriminate between them. That means good features can be retained and bad features can be eliminated. So this is the procedure. So here the first step, this is say the one typical data table that we have got. For example, different cases for different fault conditions. These are the features, 12 features, and certain we have normalized. So these are the certain values, 0.95, 0.43. These are the feature values for different cases. And for rough set theory, we have to discretize this. That means 0.95, 0.92. In this way, we should not give input. We should give in some numerical values or some discrete values. How to have this? There exists certain methodology. I am not going detail into that methodology because that mathematics is not going to give you any benefit in this particular lecture, because that mathematics is difficult. You have to give time to learn that. But I am just giving you the idea what should be the way or what should be the approach of solving the problem. So I am just giving you the steps only. So this is the step 1. That means data table is discretized. Discretized means initially it should be 0.95, 0.92, 0.44, something like that. After discretization, that will be some sort of discrete values, discrete integral values. So 0, 1, 2, 3, 4, 5, 6, like that. And then identical attributes and cases that can be eliminated. There are certain elimination methods, elimination algorithms are there in the rough set theory that you can have in our papers also. The references are given, and then you can eliminate those not so useful features. For example, in our case, F4, F5, feature number 4, feature number 6, 9 and 10, they are found dispensable. Dispensable means they can be removed. And then you can find out some important values. So initially the table looks like this. After that rough set theory, if you apply rough set theory, all the unwanted or all the say superfluous data, that is eliminated, and you can find this type of table. That means now most of the things they are removed and important portions are there. What does it mean? It means that for series fault 1, that means it is the say fault case 1. That means say it is the series fault at disk number 1. Say so for disk number 1, these are the features, they are found to be very useful. That means if you are trying to find out whether it is a, say, fault case 1, we have to check what is the value for F2, what is the value for F7, what is the value for F11. The other values are not so important in this case. In that way, initially, what is the approach? So you have the data, you know what are the limitations, what are the things to be taken care of for the data. Then according to that, you have to choose your feature extraction tool. Then for feature extraction tool, you may have several features. Now, all those features may not be useful for your case. So you have to use certain or such a tool, such a classifier that can eliminate unwanted or unrequired or say not so important features and remain, or it can give emphasis on only important features, just like this. And you can have the rule based then, or you can program it in if then else form. That means this type of if then you can have it. For example, if the rule base is if F2 is 5, this is the end, F2 is 5 and F7 is 1 and F11 is 1, then we can say it is a fault at position 1 or something like that. So in this way, you can have different rule base and you can validate it. After validation, you can employ them. So that is why, that is the beauty of, or that is the, we can say, advantage of having handcrafted features. And also, if you are having handcrafted features, then you have to choose proper classification tool. So that should be the proper way of the choosing the analysis system. Otherwise, usually we have seen our students and researchers initially when they have they are very enthusiastic of doing some project, doing some research work, they usually trying to use, say, different tools abruptly at random by trial and error method. That means use tool A, whether that is performing well. If it is well, then keep it. If it is not, then replace that and try another tool. That should not be the proper way of doing this. That means the proper way should be, you must have some idea of the data acquisition process, what are the limitations. On the basis of that, you have to have the pre-processing mechanism, or you can have the data acquisition mechanism. Then what are the features you can extract? Either you can go for say black box sort of system, or you can go for handcrafted features. If it is handcrafted features, then what are the features? They are important, that you must know. So that is why you have to choose a classifier, so that you can identify what are the features that is very useful to you. So in these logical steps, you have to choose the data. And that is why when you are writing your research paper, those steps are to be mentioned. Then only that there will be a very good research work, or we can say a solid research work. The reviewer can have all the answers there in your paper. And these are the results we can see. And we have tried this, the 91% accuracy. We have used CNN also, and we have got very high accuracy with that, but at the expense of very high computational facility. Again, the second one, that is the partial discharge. So I have shown you these waveforms, and again, this is your waveform, and again we are using, say, cross wavelet transform of this. That means, say, this is your noisy or partial discharge waveform with this sinusoid signal, and we are just doing the cross wavelet with this. That means this noisy PD pulses and this waveform, the PD signal superposed on power frequency reference. So these two signals we have performed cross wavelet transform, and we are getting this one, this diagram. Just have a closer look of this. See, you can have the beauty of this. Usually what happens, look there. In PD, what happens if we assume this as a full cycle, this left one, the figure A, if we assume that as a full cycle of a sine wave, then you can see there, in the left half cycle, one region is there where partial discharge is occurring here, and another region is there partial discharge is occurring. And other portions, all those these sort of undulations, all those noises, they are purely unwanted signals, and we can have we can assume them as noise. So therefore, whenever we have performed this with partial discharge and the sinusoidal signal, what happens? In which region we can have the similarity? In the region we having the similarity is this region. That means this from 0 to 0.02. So 0.02, that means 20 millisecond. Our household supply is 50 hertz. So 50 hertz signal means it is one full cycle, 20 millisecond. So 20 millisecond is having two hubs. One is 10 millisecond, other is 10 millisecond. So in each hub we are having this type of waveform. You can distinctly understand there occurs certain say similarity between two waveforms. That is why it is actually that cross wavelet transform actually gives similarity between two waves in time frequency region. That means it gives the colors are different, means in this region these two waveforms have similarity. So again, we just taken these handcrafted features, applied some rough set theory, and got the result. See, these are some scatter plots. You can have different cases. We have just found 4 different cases of fault locations in partial discharge void locations, and D1, D2, D3 and D4 are the 4 different cases we are trying to identify. That means D1 means say fault or void location at location number 1, D2 means location number 2, D3 means location number 3, and D4 means location number 4. So we are trying to identify from the waveforms at which location PD has PD is occurring. So D1, D2, D3, D4, these are the, so it is sort of a localization problem, we can see. That means we are trying to localize the PD site. That means we are trying to find out within the electrical equipment what is the location, where is the location the PD is occurring. So if we are trying to plot those handcrafted features, you can find in 2 dimensions they are more or less overlapped. See, different colors mean different cases and they are almost overlapped. But in high dimensional space, they can be separated. That is why manually, in manual observation, you cannot be able to identify the rules. That is why machine learning tools are required. So these are the different D1, D2, D3 and D4. That means D1 means narrow void in contact with the electrode. D2 means narrow void away from the electrode. D3 means large void contact of the electrode, and D4 means large void away from the electrode. These are the 4 simple cases I have taken. So again, the same 4 to 5 steps. Using that rough set theory, we can have the rule base, and you can see what I was talking about. Using the noisy PD pulses also, we are having acceptable amount of accuracy. Why? Because we have used a good feature extraction tool. It is not that only the classifier that can have all the good job done. That means if your data is not proper, then whatever maybe your good classifier is, your result may not be acceptable. So that is why it may not be very good. So therefore, in noisy case, I am just showing you, as we have chosen no denoising tool. So we have chosen the cross wavelet transform. That is why the noisy waveform effect of noise that was eliminated. So that is the logical thinking. That is the logical process of doing the job done. That means if you are doing some say denoising thing, then you may have gone for only purely say wavelet coefficients, only say continuous wavelet coefficients. Then from wavelet coefficients you extract the features, then you can classify. But as we didn't use any denoised, and we know that there exists some noise in the PD pulses, therefore we have gone for cross wavelet transform. And because of the reason of choice of this is to eliminate the effect of noise. So in a nutshell, we can see that the different electrical systems can be analyzed. We can have the condition of different electrical systems using different tools. You can have denoising using optimal filtering, adaptive filtering, but you can avoid that also. So it is not that mandatory that you have to follow this path. So there are different aspects, and the logical way of approaching that is the main thing. So if you are having some denoising, then you can have important, or depending upon that, you can have the feature selection. or minimal feature selection. Minimal feature selection means you may have so many features, but all of the features may not be useful. That is a very common problem. And another problem is that say feature 1 and feature 2 may gives the same thing. That means they are correlated. So it is not required that you are keeping feature 1 as well as feature 2. That means that is unnecessarily you are burdening your analysis software or analysis resources. If you can eliminate less number of amount of data means faster processing, efficient processing. And also nowadays you can have feature learning. I told you, if you know the system very well, then you can go for handcrafted features. If you do not know the system very well, then go for the black box sort of thing. And in black box sort of thing, the NN or some deep network, convolution neural network, they actually learn some features. And what are the features learned? Then you can also see. But why those features? There is no such explanation as such. But nowadays people are trying to find out explanations. There are certain methods to find some explanation why those features are very good. And what are the features those black boxes are learning? That is called the feature learning. And classification of features, you require some classifiers. Then depending upon the earlier stages, you have to choose the classifier. So in any case, you should know the background, you should know the history. Otherwise, the proper system cannot be done. So that is why the homework, that is why the earlier things one should learn. It is not that blindly you can have the data and you can apply some tools and you can get the data. That should not be the process. And if you sum all of these things and you can combine them together in an expert system, and you can have one particular tool, one particular expert system that can acquire data, that can process data, and that can give you the result. So this is one book. Again, I am just blowing my trumpet. That is the outcome, a part of my PhD research work under Professor Shivaji Chakraborty. This book we have published. And as this type of work should be done, unless you have a good team to work with, then this volume of work you cannot, because it is very difficult for one person to record the data, to acquire the data, design the data acquisition system, then again process it, then design the feature extractor, then again the classifier. It is very difficult. So that is why if you are working in a group, that is why the group working are very say successful in this type of condition monitoring works. So I am very lucky to have be able to join this kind of very good group. I acknowledge or express my thanks to all the group members and my guides also for doing this work, or making me able to doing this work. And thank you for patience hearing. If you have any question, you can ask.
Thank you, Devanshu. Am I audible?
Yes,
madam. Hello?
Yes.
Okay. It was an excellent presentation, and I'm pleased to share with you that more than 80 participants were watching you live in YouTube. They have posted.
How many?
More than 80 participants were watching you live in YouTube.
Okay.
And the questions have been posted in the chat box.
Okay.
There are questions. I would request Komalika madam to read out the questions. She is a faculty member of her department. Yes. She would read out the questions for you.
Yes, madam. Thank you, sir. So the first question has come from Devmallo Pramani. So he has written, respected sir, can you suggest some good books regarding condition monitoring of transformers? So this is the first question from Devmallo Pramani to you, sir.
Okay, and that is very, I'm happy to answer, because that gives again a very good option for me to give me opportunity to blow my own trumpet again. So this is the book. I am just sharing the screen. This is the book. This is specifically for transformer condition monitoring. This is specifically for transformer condition monitoring. And as this is just almost just covering all the recent topics, we can have this. But nowadays it is published in, say, more or less, say, 7 years back. But still, no, the further papers are there, but books are very limited on that. So you can go for this book.
Okay,
Sir,
thank you.
the
And
second question
next,
from the second question from the same participant: what are the available methods for designing equivalent circuit of the transformer for insulation calculation?
What are the different?
What are the available methods? What are
Okay,
the
available methods.
available
Okay,
methods
okay.
for designing?
Okay. And that available methods, there are so many different methods. I am just showing you that one of this type of method is this one. I just shown you this. Yes, this one. You can have the Debye model for that. If you are trying to analyze the transformer insulation modeling, so that Debye model is very good, and there are different papers available from our lab, from our Jadavpur University high voltage engineering lab. You can have different papers. If you can search IEEE transactions, there will be several papers under the guidance of Professor Suresh Chakraborty. These are the different types of insulation modelings are there. Those papers are very good, as they are very say frontline research topics. So they are not been published yet in a book, but you can have access to those research papers. The Debye model is a good model. It has nonlinear and linear modelings aspects also. You can have the linear model consideration, you can have nonlinear model, you can have the frequency dependent model, etc., etc. So you can go for these papers.
Okay, sir. Another question has come. Any software or methodology for simulating transformer condition monitoring? Any software simulator available for simulation?
One software is available, but all those softwares are very costly and proprietary, because they involves lot much of money. Why I am telling you that? I told you that nowadays transformers have reached their age of the design life. So one transformers, even very moderate size transformers, costs about 1 crore of rupees. So therefore, if you can have a software or analysis tool that can analysis the condition and tells you that whether you have to replace the transformer, or you can use that can save you crores of rupees. So all those analysis softwares, including the instruments, they cost say around 20-30 lakhs. So that is why softwares are available, but they are costly. But if you know how to model it, then there are certain, you can use them in EMTP, you can use them in any other, say, Python programming also, you can do that. If you know the inside story, that means if you know, if you are an expert on this, you can model that. But otherwise, analysis software as a whole, they are not free. All of those softwares, they are actually proprietary.
Okay, sir. Now, another question has come up from Pratyusha Bishasdev of our faculty of our department. She has asked a question: what can we take the steps for load variation and clamping pressure in clamping pressure low in data transformer monitoring? I repeat the question once again. What can we take the steps for load variation and clamping pressure in data acquisition system of transformer monitoring if we consider moisture?
Okay, there are different ways of doing that, and that type of it depends which type of data you are trying. I have shown only the PDC, but there are other ways of taking the data, that there exists certain frequency domain spectroscopy also, and also you can reduce the time of data acquisition by some means. It depends, that methodology depends on in which what is the method you are using for the data acquisition. Depending upon that, you can have. There are certain methods, methodology that are told in research papers as well as in our book also. Then if you just mail me, I can send some materials, because there are some descriptions are there. Just you have to go through that. So that is why in each of the different methods, for example, if it is PDC, there is something else, and if it is FDS, there is something. So that is why in this way you can have the answer for that.
Okay, sir. Sir, another question.
Hello, are there any more
What
questions?
is the one question, what is percentage impedance of transformer? What is percentage impedance of transformer?
No, that is, I mean, in my case, I have just taken that model, and when you are using that impulse response, that impedance you found in your transformer, transformer, say equivalent circuit, that impedance will not come. So that question is irrelevant in case of this condition monitoring of the transformer. That's why we usually measure the geometric capacitance also, but that impedance is not very which you just learn in your UG course. That is not important in this case.
Okay, sir. No more questions now.
Okay.
Okay, thank you, Kamalika madam. And
Thank you, madam. Thank you,
thank
sir.
you, Devanshu. That was a wonderful lecture.
Thank you,
Okay,
Navamita.
so,
Thank you all.
and what we can do from our end in this digital mode of faculty development program, we can present you a token of appreciation for our end. I'm going to share a screen with you. Please wait for a while.
Okay.
I'm sharing a screen
Okay.
of token of appreciation from our end. Okay, so this is a small token of appreciation from our end. Can you see, Devanshu? Can you see my screen?
Just it is coming. It is coming. Because okay,
Okay,
yes,
okay,
I can
coming.
see now. Yes, I can see now. Okay, it's very nice. Okay, thank you. Thank you.
Okay, okay, we made you the same. Okay. So
okay, thank
this
you.
Is a new method of showing appreciation. This has come up as
Yes.
a new method of showing appreciation.
Yes.
Okay, and
Very nice. It is
also
very nicely designed.
the YouTube broadcast. Thank you. And the YouTube broadcast that we have chosen, we just decided the other day, yesterday, we were giving trial. Okay. So this proposition came from the faculty members of my department only, Mr. Akintu Mitro, Mr. Pallav Datta, and Mr. Sudhanshu Sarkar. And I think this system went well. You know, it was noise free. I hope you didn't find any interruption, right? No noise, I think, because the presentation went on very smoothly, I suppose. Okay, that was the main objective of making the YouTube broadcast. Okay, so thank you, Devanshu, and thank you to all the participants. So if there are no more questions, I once again see our controller section. Controller side is there. Professor Amrut Chakraborty is there. He is a controller of examination in our institute, as well as he is a professor of our department. I would request Amrut sir to say a few words before concluding this session. Sir, are you there? Is he there? Okay, I don't think he is there. Anyway, so Devanshu?
Okay.
Hello?
Hello.
Okay.
Yes.
Okay, Devanshu, I think, okay, so I think he is not there. So
Okay.
once again, thank you all, and thank you to all the participants who were for your patient hearing. Thank you to all the entire team of Narula. Kuna sir is there. Professor S.C. Konar. He is a professor of our department. Konar sir, are you there? Can you say a few words to Devanshu? Hello, sir.
Hello, Professor Devanshu De.
Yes,
Good
sir.
afternoon. Good
Okay,
afternoon.
very good afternoon.
In your nice speech, you are telling first of that impulse,
Yes, yes.
and second time in continuation of that, you have to tell that step. But
Yes.
impulse of magnitude will be required to specify for the rating of the transformers.
Yes, yes, yes. Depending on, as
And
per IEC, that's why I have just mentioned. As per IEC, depending upon the rating of the
and
transformer.
also another question:
Mhm.
what is the better response if we compare the impulse as well as of the step response?
Actually, sir, what happens is that the purpose of doing these are two different aspects. That means if we are trying to find out the overall insulation condition, that means if a transformer is working up on the normal, say, power frequency voltage, and what is the insulation condition, then we should go for that PDC. So we should apply the step voltage, and then again we have to record the discharge current shorting that voltage. So that is one purpose. And another thing is that if we are trying to find out what is the impulse withstand capability or impulse withstand ability of the transformer insulation, then we should go for the impulse test. So therefore, two tests, they have their own advantages and own requirements. So that is why one cannot replace the another.
That depends on the rating of the transformers, power transformers.
Yes, for all of the rated transformers, the impulse for it is if it is say 3 MVA transformer with say certain say 33 kV, then the impulse voltage standard is given. Now, if we that same transformer, if we are trying to understand what is the condition of the overall insulation, not the impulse withstand, then we should go for the step one. Again, the rating will depend.
Okay, thank you. Very nice lecture delivered by you.
Thank you.
Okay, thank you. Okay.
Okay, thank you, Devanshu. And some of the participants have asked to ask for email ID. Okay.
Yes, my
And,
email ID.
Okay.
I am just sharing that. Just a minute. I am just sharing it quickly.
And also your presentation, if possible, in PDF.
Okay, I can send you the presentation, no problem. Is that visible?
Yes, it's visible.
Is the bottommost line, that is my email ID.
Yes, yes, it's visible.
If you send the request for this presentation, there I can send the PDF file.
Okay, I hope the participants have got it.
Okay.
Okay. So how was your experience today in the online version?
Yes, that is very nice and very smoothly run. That is very well organized, I should say.
Okay. Okay, thank you.
Thank you being
once
here
again.
and interacting
Okay.
with all
So
of
is
you.
there okay, so if there are no more questions, and with the permission of all, as well as the speaker, so shall we close the session?
Thank you. Thank you all.
Okay.
Okay.
Have a good day.
Okay, bye everybody.
Bye. Goodbye.
Thank you, sir. Bye. Thank you. Thank you. Thank you all.